Welcome everyone to our 7th colloquium on public interest technology. Today we're dedicating this 2-hour block to truth, fact, time. And we've got a triple header here. This week we're going to spend 2 hours with Dr. Michael Eldred, who's currently coming to us live from Germany. In a fortnight, we're going to have Pascal Zachary speak to us on a historical point of view on the future of innovation. And in a fortnight after that, we're going to seek out a theologian. So philosophy, history, theology. And today's 2-hour block is focused on philosophy, and we have the wonderful Michael Eldred with us. Today's meeting is brought to you by the Society Policy Engineering Collective, SPEC, the group that I direct, at Arizona State University. It's brought to you by the School for the Future of Innovation in Society that I belong to. And also, this video will be played and broadcast to the International Symposium on Technology and Society. That's ISTAS, that's happening between the 12th and 15th of November, virtually, online. Please, if you'd like to attend ISTAS 20, that's dedicated to the theme of public interest technology, do contact me at katina.michael@asu.edu. I'm your chair for today. I'm also the chair of the Masters of Science in Public Interest Technology. And that's an online degree that we offer that inspires both humanities and social science scholars to dabble in the STEM. It also inspires STEM scholars to become more fluent in the areas of humanities and social sciences. And so coming together, what we're hoping to do is to build a robust group of practitioners, applied scholars, and even theorists in this new emerging space of public interest technology. As I mentioned, we have Michael today, who I'm dubbing the philosopher, though he's also a mathematician. Following him will be Pascal Zachary, formerly of Arizona State University, a historian, but also a journalist. And 2 weeks after that, I'll surprise you with hopefully a theologian. So Michael, I'm going to stop sharing my screen and welcome you formally and say hello. You herald from Katoomba, New South Wales in Australia. You met MG Michael some years ago, my husband and collaborator. I welcome you to the colloquium.
Thank you. It's very nice to be here. And thank you for giving me the opportunity to speak to several people at once.
It's a different kind of format. You know, the last 6 weeks, we've had a great time together. Middle of the night here in Australia, 3 a.m., I think, and late evening your time. And we've been jamming about all things philosophy. We've been jamming about things like what you call interplay and productive movement. You've blown my mind. And I'm just sitting there thinking, where has this philosopher been in my life?
Yeah, today, as you say, we have now the topic of truth, facts, and time. So this is going to be philosophical. And I want to do a couple of phenomenological seeing exercises with you. Everybody knows what a fact is, and everybody knows that we talk about facts being truth. You hear politicians talking all the time about, well, the reality is this, the reality is that, and we got to look at the facts, right? This way of speaking actually has a very long tradition, and it is due to our old friends Plato and Aristotle, once again, because we have with Aristotle that he treats different modes of being, and he says that truth is a mode of being, and he goes proceeds by saying that the truth is situated in the statement, or you'd say the statement. He calls it the logos. The statement in philosophy, in mainstream philosophy, it's called the proposition, and this has been a long tradition of how you investigate the truth by investigating statements. You look at how these different statements hang together, and if you proceed from true statements, which are called the premises, and you use the proper rules of inference, then you come to a conclusion that is true. And this is something I think you, not only in philosophy but elsewhere, you learn. This is the method of arguing from true premises to true conclusions, and they can also be false. But the question is truth really situated and located in statements, or the propositions? And I'd just like to give you a very simple seeing exercise, a phenomenological seeing exercise, to see if that's the true state of affairs. Now, over here in the corner that you can't see, there's a chair over there. So if I say this statement, there's a chair over there in the corner, is it a true statement or not? Well, you can't see the chair, but I can look around and I see the chair in the corner and I say, and for me, it's immediately clear, it's true. There's a chair in the corner. And this is how I test the truth or otherwise of the statement, by seeing. And in this case, it's seeing immediately. I see it with my senses, with my eyes. And I just say, well, there's a chair in the corner. That's so the truth of the matter depends upon what I see. But I can also say, oh, there's a chair in the corner over there, and I know that because I've seen it several times. You know, it's a fixture of the room, and I just say it. So this is referring not to something I'm looking at immediately now in the present with my eyes, but I'm recalling it from memory, and my memory is not too bad. So it's true in that sense. It's true because I see it not with my senses in the present, but I see it in my memory, and my memory is okay. So there's a difference there, that you, when I say there's a chair in the corner, I'm just saying the statement, and you can say, well, I don't know if that's true. I don't know if that's true because I can only take your word for it. So you think to yourself, well, if it's a reliable source and I'm not lying, then okay, the statement holds. I believe you, and you're a reliable source, and you're not a crazy man, and you're not someone in the White House. Now, this is just to point out that the truth of statements, so the truth of the logos, is not situated originarily in the statement itself, but it refers to something, to a situation, and you have to get this situation before your eyes. And you can get that before your eyes in the sense of looking at it in the present with your senses, or you can rely on your memory and call it up and say that's the way things are. The second example I want to give, which is a little bit different, but it's to do with the difference between truth and fact. Now, what I just said about the chair in the corner, this is a matter of fact. And when I say there's a chair in the corner, I look over there and I confirm that this is a true fact. It's correct. What I say is correct in that it corresponds to the way things are. And this is also a traditional way of thinking about truth, that the statements you say correspond to the way things are. This next example is another phenomenological seeing exercise. And now I will show you something. I'll show you this. It's a pen. You can see a pen, I think. It's also something. This pen is a something, and I show it to you. And okay, you can see it. It's a pen. Then I show you something else. This is a knife. This knife is also something. So I'll show you both. This is something, and this is something. They're both something. In the sense that they're something, they are the same because they're both something. And they're also different. And this is something and this is something else. So we understand that. There's no problem. There's no problem. We have no problem deciding this is something and that's something and this is something and this is something else. And we take that for granted. But where is the something? We understand already beforehand, so prior to seeing anything at all, that we can identify something as something. And this is very strange because the something itself, the something, simply this category of something, is not something that you perceive with your eyes or with any senses at all, with any of your physical senses, but it's something you already see with your mind's eye beforehand. And without that being able to see this category of something beforehand, you wouldn't be able to identify this as something and this is something. And the same goes for the category of seeing something and something else, the other. We already know and understand completely without thinking about it, taking it for granted, that we can differentiate between one thing and another, the something and the other thing. And this is what Aristotle calls a category. And the category is a Greek word, comes from the verb kategorein, which means to address something, and especially to accuse something, to accuse. So you have the situation where I accuse this of being something. And this category of something itself is what I already bring to the table beforehand, before I see anything. So it's before any empirical experience. And this is where I want to bring in the distinction between a fact and truth, that there's a change of levels. The facts have to do with things that you experience empirically, and you can establish whether they're facts or not. But the truth of the matter refers to something deeper. It refers to how your mind already has certain categories available to see the world, to see something as something, to see something other as something else. And this is the dimension which we tend to overlook. Not only tend to, but it's something which is in the modern era, in our modern scientific area, which is skipped over altogether and says, well, that's obvious. It's trivial. It plays no role. We just say it has to do with what they call speculation. This is just speculation. And it's interesting that the word speculation itself is the Latin translation of the Greek word theoria, theory. And the word theoria comes from the Greek word theorein, which means to look at, to contemplate, to look at. But it's a looking at which is not sensuous, it's not dependent on the senses, it's a looking at that is, in that sense, speculative, but it's completely clear. It's not fanciful thinking. It's not simply a product of your imagination, but it's you actually seeing, for your mind already sees the category of something. So now I want to make with these two examples that truth itself depends first of all upon seeing phenomena, and phenomena, another Greek word, which shows itself of itself. We see phenomena, and the truth of a statement depends upon the phenomena showing themselves. And if the phenomena do not show themselves as they are, but deceptively, then there's a kind of hiddenness. The phenomenon in question is then obscured. And this is something, again, different from the formal logical way of going forward, is to say that if you have true or false premises. And once within formal logic, you argue, you assume the premises are true, and then you infer from these premises certain statements, and you come to a conclusion without any further reference to phenomena. And this is the way, say, mathematics works, or at least formal mathematics, is that you have true premises, they're called axioms, which seem to be self-evident. And then from these axioms, you derive by rules of inference which apply to that mathematical entity and come to properly inferred conclusions. And these are the theorems of the mathematics. But what I'm saying is that the theoria, the depends on seeing the phenomena themselves. And this capacity to see the phenomena themselves is what Aristotle calls nous, which is translated normally as, well, you have the English word nous, which means reason. And reason, or the mind, is the faculty called the mind that is able to see phenomena, immediate phenomena, which just by looking at them, you see them. And the example I gave was the category of something. We see that with the mind. And it's true because this is the, it's very hard to put the category of something itself into question. Now, I'll make a big jump to modern science, and I'll take the example of the Einsteinian relativity theory. You can have the special relativity theory or the general relativity theory. Let's just keep it simple. We stick to the special relativity theory that Einstein developed at the beginning of the 20th century. And he develops this theory. There was a whole kerfuffle in mathematized physics at the beginning of the end of the 19th century, beginning of the 20th century, and was to do with how do you deal with light, or more generally, you'd say electromagnetic radiation, because light has lots of different frequencies. But I'll just talk about light for the sake of simplicity. And here we have, in 1881, we had the two physicists, Michelson and Morley, showed by a very sophisticated experiment that the speed of light didn't depend upon the frame of reference it was being measured in. And you normally expect that if you, in normal situation, if you're riding a horse at say 20 kilometers per hour, and a train is passing you by because you're riding alongside a railroad, and it's going at 100 kilometers an hour, then you'd say the train is going at 80 kilometers per hour compared to me on the horse who's riding alongside the train at 20. Whereas for someone on the ground just standing there, the train is traveling at 100. So there will be a relativity in that. But what Michelson and Morley established was that in the case of light, there's an absoluteness about it, is that it doesn't matter. Your relativity to it, it's an absolute movement and has an absolute speed, which is the speed of light, c. It's called c, and it's put in all the equations as c. And from this fact, it's an experimentally established fact, established by a very sophisticated experiment. Einstein took this seriously and said, okay, well, this speed of light and light itself is the only thing we've got going for us. If you're a physicist, you are interested in physical phenomena, and for physics, and especially and quite explicitly for Einsteinian relativity theory, and he goes back to very the tin tacks and says, well, what does it mean for an event to happen for a scientific observer? Well, it means that the observer has to register some sort of physical event somewhere happening at a certain time. So you have 4 coordinates. You have the 3 spatial coordinates, X, Y, Z. You say Z over there. X, Y, Z, and T for time. And he notes, okay, that's for a nicely ordered scientific mind, that's great. You have to register the events at a certain time. And it may be that this event can only be registered, you can only receive it, not directly by looking or smelling or hearing it. You might need incredible apparatuses, such as enormous telescopes, or you might need the Large Hadron Collider in Geneva. But in any case, the basic situation is you are receiving a signal from the event that is happening, and you register it. And this signal itself can only reach you as an electromagnetic signal, which I'm just calling light. So you receive a light signal as a scientist, and it is only when this signal is received and you count it on your clock that the event is then registered as happening factually, true to the signals that you are able to write it down, or in these days it's registered by the apparatus itself. It has a timestamp on it. So you've got 2 things going on here. You've got time itself being understood as the reception of a signal. And this signal is counted according to the clock time at which you register it. And this is the way physics has to work, that it's sensuously received either by the observer's own senses or indirectly via the apparatus, because in the end the scientist has to see the data from the received signal. And you've got this postulate of relativity theory to say light is the absolute movement. And this remains so to the very day, that light, reception of signals, is regarded as the absolute registration of time itself. So in a way you have time itself, which is just the counting of movement, becomes a movement itself, namely the movement of light. And this is the way physics proceeds, and even with general relativity theory, where you have the light signals can be bent, and this is also an experimentally established fact. I'm not saying it's true. It's a fact that there are observations of light being received from outer space where it can be established that the light coming from outer space has taken a bend. It's or a curve, you call it, or a warp. And this is the origins. This is the origins of Einstein's general theory of relativity. So on the one hand, you have the special relativity theory, which says, okay, light only goes in straight lines. We assume that the light is not accelerating. It's a steady straight ahead at the rate c. Speed of light 300,000 kilometers per second. So it's the 1 second, you can say, is the distance between the Earth and the Moon, because that's roughly 300,000 kilometers. So what is time? Well, 1 second is the distance from here to the Moon. So you've got this transformation of time into a movement, namely the movement of light, and how 1 second is the distance that light moves within 1 second. And the general relativity theory, which takes into account that there's acceleration going on. Well, the only acceleration that light can take, because it has it can't go faster, it can't go slower. That would be accelerating or decelerating. The only way light can accelerate is by changing its direction, which is what it does when it takes a curve. And this curve is what accounts for this wonderful and very strange phenomenon of the warping of time-space, which is still fascinating, that relativity theory says to us, because of the bending of light, the universe and everything in it is subject to this curvature of time-space. So this is really strange, and it depends upon gaining a mathematical access to the world. And this gaining of a mathematical access to the world is not something that was there from the start. Although you might say, even with Pythagoras and with Plato, you have the rudimentary beginnings of this attempt to gain a mathematical access to the world. But it really takes off at the end of the medieval times, when in the Renaissance, beginning already in the, well, say the 16th century, you have an incredible development of mathematics. Some really incredible things going on. You've got, for example, just as an example, you've got Cardano, an Italian mathematician, working on certain sorts of equations, trying to find out the roots of certain equations in which exponents of 2 and 3 and 4, square the quadratic equation, a cubic equation, quadratic equation, so on. He came across the necessity in improving or trying to find the roots of certain sorts of equations. They had to introduce an imaginary number, the square root of -1, because it was known that you can't have the square root of a minus number, because any number squared will always give you a positive number. But he did it anyway. So you got this introduction of a concept which is not sensuous at all, but it's a concept in mathematics that is seen by the mind, and you can actually work with it. And thus were imaginary numbers invented by the mind, and also in the sequel from that, you have an incredible burgeoning of mathematical thinking on complex numbers. At the end of the 16th century, going into the 17th century, you then have Galileo, and a little then and Descartes, and a little bit later you have Newton. And they, especially Newton is probably the most famous in the English-speaking world, they proceed with this program of consolidating and extending this mathematical way of accessing the world. As so you have, for example, you have the famous equations of Newton. Three extremely simple equations that are able to account for physical movement. I mean, first of all, it was developed by contemplating the movements of the heavenly bodies, so stars, planets, the moon. And with these very simple three equations, you were able to account for the movements of the planets. But this was then generalized, and it was said that all you need really is a homogeneous space, and it has to become homogeneous because you want to describe it mathematically. So you have three coordinates, x, y, z, and these are the famous Cartesian coordinates. So it's associated with Descartes, who also worked in this area. So you have this is something you did at school, and with great interest, of course. And you first in school you do it mainly with in two dimensions. You have x and y, and you have a curve, and so that's the way that you account for space. And it's not just outer space; it's not just the heavenly spaces way out there, but it applies generally everywhere. You can pinpoint the position of anything through providing the three spatial coordinates. And then on top of that, because you're interested in movement, and physics is the science of movement, of things that move. And this is already something that is quite explicit with Aristotle. Physics is the study of things that move or can move, the movable. So you have the adoption of this Greek understanding of what physics is. It's taken over, and Newton then develops his theory of motion. And I say motion in distinction from movement because motion you have to understand as the change of place. So it's locomotion, change of place. Whereas Aristotle, in his physics, he doesn't have only movement in the sense of locomotion, change of place. He also has the qualitative change in something, say when the leaves on the tree turn from green to brown and then fall off. This is a qualitative change. Or you also have the phenomenon of grass growing or a tree growing and also decaying. So you have growth, and you have the fourth mode of movement, according to Aristotle, is that of reproduction or progeneration, where one being reproduces itself in another being, which is the most complicated kind of movement. So what this modern physics tries to do in its program for mathematizing the world and getting it into an equation is to attempt as far as possible, and it's got very far, is to attempt to conceive all sorts of motion, all sorts of movement as motion, all sorts of movement as locomotion, change of place. Because then, if you have locomotion, then you can write equations with it. And you write equations in terms of a parameter or a variable which you call time. And there's always this little t in the equations. And this t is magical because with it, you can actually calculate motion. So you have, when something is flying through the air, a missile, or could be a planet Jupiter moving across the sky, or a bullet speeding through the air. This is locomotion. And you have, with Newton's three wonderful equations, you have a way of calculating what this movement will be and being able to predict through the equations where the bullet will land, or you can operate with the orbit of Jupiter and calculate where Jupiter will be in 10 years or 1,000 years, whatever. So it all depends upon this little variable in your equation called t. So what's t? T stands for the instantaneous speed of something at this point in time called t. So it depends upon conceiving time as a flow, an instantaneous, a flow through which you can measure any kind of motion. So you have the instance of times are coming through from the future and going into the past, and with this time that is just a continuous series of instants, of now instants, you can measure and tally any kind of motion. But what is an instant, and how can it account for motion? And this is quite a puzzle, because we know also from the Greeks, also from Zeno, who was one of the pupils of Parmenides, one of the first Greek philosophers. Zeno enunciates some of his paradoxes way back in the 5th century BC. And one of them says, consider an arrow. Today we'd say, consider the bullet of an AK-47. So let's keep it simple. We just go with the arrow flying through the air. And he says, at any instant in time, the arrow is at a standstill. At any instant in time, it is at a standstill. So how can it move? And he concludes, well, it can't move because instantaneously it is at a standstill. So there can be no motion. And this paradox recurs with the mathematics and the mathematical physics inaugurated by Galileo, Kepler, then Newton. That you have equations, but how can you deal with motion if you have every event happening at X, Y, Z, T? So how can you have motion? And this is where the famous differential calculus comes into play, that you can only take an average speed of anything. We measure speed by saying we cover a distance in a certain time. So you've already got the motion in there. And in order to get to the motion or the instantaneous speed, you take this average over a distance in a certain amount of measured time, and you make it smaller and smaller and smaller. And this is where the infinitesimal calculus arises. So I have Newton developing his version of infinitesimal calculus, and on the continent just nearby where I am, well, I'm in Cologne, and Leibniz's hometown was Hanover. He developed his version of the differential calculus, which operates with infinitesimals. And that works. It's effective. It actually enables the physics of that time up to the present day to calculate and to pre-calculate how motions go. But there's still something paradoxical about considering time as this flow of instants through the now, and considering an instantaneous speed when Zeno says, well, anything at an instant is at a standstill.
Can we break and talk about that, Michael? Because I think Zeno's paradox is fascinating. And I also think there would be a lot of questions on what is truth, what is aletheia. Lots of questions on this triangle of speed, distance, and time you're introducing us to, and the relationship between these three variables. The modern interpretation, if we take aletheia and look at what's happening today in social media land and beyond, the use of apparatus that you mentioned, like global positioning systems or watches that actually take date timestamps, location stamps now, condition stamps, and our handsets having 14 different sensors in them at minimum today, doing things like measuring things with a gyroscope, an altimeter, an accelerometer. These phones know whether we're going upstairs, downstairs, whether we're huffing and puffing, whether we're stressed, whether our heart rate is rising, whether our temperature is rising. And this jam-packing of this measurement that's occurring from the physics side, our instrumentation is so accurate down to the dotted line, down to the dot, and this notion of stillness while we are moving, and we'll never ever get, one of the things my late mathematician teacher in grade 11 and 12 taught us with Zeno's paradox, you can always halve the distance, you'll never get there. And I, in my research, have brought together with M.G. Michael this notion of ubervalence, which looks at the identity of an individual, the something, but you and I have called it the being in our past conversations. We've looked at the location, and the location as well, requiring not only an X and Y coordinate on the Earth's surface, but a timestamp as well as other parameters. And then we've had the condition monitoring, which is this jam-packed explanation of the person in a given instance of time. And we can measure this continuously or discretely. And the discrete nature of these timestamps, and maybe I'll log you, Michael Eldred, every 10 seconds or every 5 minutes or every 6 hours. It depends how often I want to poll you, because maybe there's a COVID virus out there that needs to know in which direction you're traveling and whether you're going toward a COVID hotspot. All of these things that researchers are thinking about in terms of the gathering of facts and the gathering of information or data that might infer something about someone. And so I find it very interesting, while we're measuring through time people's movement, as you say, we are then trying to use what's happened before and is happening now, allegedly now, to infer what's up here, to infer what is in the mind, and therefore make a decision based on someone's perhaps innocence or criminality, based on their discrete movements over time, as if those things can predict the future. And I find the fundamentals of everything you're talking about crucial, because today we have these, as you called it, modern science. We've spoken about it as techno-science. Sometimes we've spoken about it on our videos as techno-solutionism. But this speed, distance, time conundrum, which we just need two of the three and we have the third, is all much integrating in truth, is integrating in authenticity. A couple of weeks ago, I had the grace of speaking with Dan Gilmore, a journalist from the Cronkite School at ASU, and also Christy Roschke. And we were talking about, how is it that we can authenticate when information is created? And it's not just the timestamps and the date stamps and the location stamps, but how do I know that what Michael Eldred is saying is true? How do I know his perspectives on Newton are correct? And we see this, as you made a very interesting joke about the White House at the beginning, a pertinent time to make a joke, but, we're saying that in jest, of course. And what is truth? That famous question that Pilate asked Jesus Christ just before he announces the crucifixion. And so does he do it because he really wants to know, how do I know whether you're telling the truth? Like the doubting Thomas wanted to touch the side. He said, unless I see him, I'm not going to believe he's resurrected, right? So he wanted to take the matter and touch to see the actual reality. Like, you pointed me to the chair. I don't believe you, Michael. There's a chair next to you, but I trust you. So yeah, all right, I believe you. And so I think we're all in the context of taking your very deep philosophy, and I know you've broken it down so simply for us, but if it's okay with you, I want to break to get perspectives from the wonderful people that are listening today. Feel free to unmute, friends, or have your questions in the chat, and we'll just take a small juncture before we let Michael continue with where he's going with this. But I would like to hear from you. Feel free to unmute or to write down your questions, and we can pose them to Michael, or your comments or your reflections.
Dumbfounded.
Well, I tell you what, I said to a friend on the chat, Michael, that often it takes me days after we've spoken to be able to take the simple things that you're breaking, well, the complex things that you're breaking down simply for us. It just, my mind's ticking days after we've spoken, because I'm trying to latch on to these philosophical principles and apply them to what we know today. Here's a question from somebody. And as I said, I'm not a philosopher. So I struggle sometimes, but I know that by listening to you, all of a sudden you've made sense on value chains to me like never before. This interplay between individual players in a value chain. This is from previous discussions. Today, you've really broken down to me this notion of instance, this notion of continuity, and how I applied in my own research when allegedly I'm doing tracking experiments, or we're looking at pandemic viruses. The application of philosophy in the public interest is huge. And here we are trying to dial down the importance of philosophy. And like you've pointed out in the past, why aren't we trying to build philosophy in to these STEM programs rather than watering it out, when this is the fundamentals behind mathematics, this is the fundamentals behind physics, this is the fundamentals behind STEM is philosophy. But let's go to a question, Michael. Toby Shoref has asked, we talk now often about acceleration. How might this relate to time, to measurement, to technology?
Well, am I on?
Yes, you are. Go ahead.
Yeah. So, well, acceleration, as we know, well, if we take it in this mathematized sense, you have the speed is the speed in Newtonian mechanics, and not just there, but the speed of anything is the rate of change of its position. The rate of change of position. That's why you have these equations dx dt. So it's an average speed reduced to an infinitesimal. And as you know from school, the acceleration of anything that's in movement is the rate of change of the speed. So it's the second differential. So it's the rate of change of the speed. So you take dt, dx dt, you take the second differential, and this is your acceleration. But the curious thing is with the Einsteinian theory, where you have light as the absolute speed, there's nothing to differentiate. There's no change. There's no change of speed of light, of c, because it's all c. Light is pure energy, or you can say light is pure motion. And if it's stopped, it's not in motion, or it's absorbed as an energy by something else. So the only way light can accelerate, which it has a rate of, it can change its rate of change of its position only by changing its direction. So that's why, and that's where you have the rate of change of its direction is what you call acceleration. So light can only accelerate by taking a bend, by warping. And this is the origin of Einstein's general theory of relativity. The bending of light is the same as the warping of time-space. I mean, that's the really strange thing, to get used to that. The bending of light is the same thing as the curvature of time-space. And you have to try and get your mind. I'm not saying you can't get your head around it, but you can get your mind around it. And there are some very complicated mathematics that Einstein developed to cope with that. Once if you've got light going in just straight lines, then you have a relatively simple mathematics. You have to be able to combine the x, y, z with t. And these are the famous Lorentz transformations. Okay, you can cope with that, and the mathematics aren't all that bad. But once you get to the warping of time-space, you need things called tensors to cope with the mathematics of how the spatial coordinates, x, y, z, relate to t in a tensor. So you have, instead of having a flat space through which light goes, you have a curvature, like if you take a sphere. This is where these Riemann tensors arise, by considering the curvature of a sphere, and then you can describe that mathematically, and then you're off to the races with general relativity theory. So that's the answer to what acceleration is. What I wanted to say next was about this whole program, which really takes off in the 15th, 16th century, 16th century, 17th century. So it's really, really underway in the 17th century with Descartes, and Descartes actually writes down what the plan is. What is the blueprint? What is the blueprint? And he writes a thing in Latin called De Regule, about rules. And the full title in English, it would be something like about the rules for giving orientation to the mind. And there he lays out what the mathematical access to the world has to look like. You have to be interested in quantities. And the examples which you've just been talking about have to do with the leading edge of what's happening today. But what's happening today is just the leading edge of a wave that started at least in the 17th century, and you could say it started already with the Greeks. Because why? Because knowledge understood in the Western sense is always a knowledge of what comes. You want to be able to say, if I know this, I want to know what's coming. I want to know the future. And this is the whole thing about the mathematization, is that if you have a mathematized time in an equation, then you can calculate what's going to come. It's prediction. And you'll find throughout science today, and not just science, but everywhere, everybody's interested in what's coming, in the prediction. What are the prediction? What do the surveys say, the polls say for the outcome of the US election? That's just one example. And you're trying to get a handle on it by using mathematics. And the paradigm for that in the modern age are the Newtonian, the three simple Newtonian laws of motion. You've got this mechanical way of predicting what's coming, in the sense of you can predict where something's going to land. You can land a spacecraft on the moon, and it will be within 10 centimeters of where you calculated it could be. And I want to make the link here that this whole drive for the mathematization of the world, and we're living in in a world that has been progressively mathematized now for several centuries, and it's now in the stage of its algorithmizations, where we get in a digital grip of the algorithms being able to. And the algorithm is just one form of mathematics. It's digital mathematics, and it's all to do with the logos. And the point is, what's driving this? Why the hell are we interested in this mathematized point of access to the world? And why is it that time is regarded as a variable that is linear? Well, what's the answer? The answer is this linear time. Linear time is one-dimensional. You have a future down there. You've got the famous arrow of time. You've got the future down there. It's pointing, and you've got the now, and then you've got the past. Right? It's linear and it's continuous. Great. Why? Well, I'll tell you why. Because we're interested in cause and effect, and if science, in our Western sense, episteme is what the Greeks call it. We study that in philosophy as epistemology, theory of science, is that science, to be science, has to work with linear time and, together with that, with efficient causes. Cause, effect, cause, effect, cause, effect. And if you don't have cause, effect, and paired with that, linear time, that's measuring it. It's just measuring it. This happens, and then this happens, and this happens. When? I'm counting it. I'm counting it in the seconds, or the milliseconds, the nanoseconds. When? So time itself is just a derivative. It's a parameter counting off motion, the local motion, preferably, because you can register that. And why? Because you're interested in cause and effect. And why you're interested in cause and effect is because you want to control motion, and you want to control all sorts of movement. So this is the will. This is the absolute will of science and of technology, is to be master of all sorts of movement in the world. And that's why you need linear time. That's why you need it, because otherwise you can't mathematize it. And that's
or monetize it. Or monetize it, right? In our first discussion,
that's the next step. That's the next step. Yes,
that's the next step. Well, the thing is, why do we want to accelerate more? In the last discussion we had, we spoke about the hockey stick effect, and we're always seeing these growth charts, which don't seem very human or humane. They're always going to be more of something. There's something you're telling us about. And we are always trying to rapidly develop faster. And now we have rapid prototyping and agile methodologies. And we want to do things yesterday because of this linear. And we look at, even now, we don't look 20 years out. We look at shorter sort of business cases. I remember when Nortel, the company I work for, went from, your 12 to 25 years for a payback period of a 2G or 3G network to something like, folks, we've got to look at 3 to 4 years because the banks won't lend beyond that time. We can't see clear enough. But anyway, we're going to do this within 3 or 4 years anyway. So, let's accelerate that payback period. I remember Michael being in a shortlisting meeting where the CFO of a large Asian organization said to me, I don't believe your numbers. The payback period should not be this. It should be this. And I'm looking at him thinking, how can it be this when it's impossible based on the facts? And so I think some of the corruption, some of the deliberate acceleration in terms of payback periods or net present values that seem to break even in a shorter time frame are leading us down a modality which says keep buying, keep upgrading. We're doing planned obsolescence and these things will come out faster. And we're going to go from this to a brain implant, from a brain implant to nanobots, like 20,000 of them in the body. It's like this almost, I think you called it once a fetish, if I'm not mistaken, or you called it like a preoccupation with the next. And you're saying in one of your first talks of what we established as a mini series based on your book, that why is it about the productive movement, the generation of transactions, the hockey stick effect? Shouldn't it just be about us and each other? The fact that we are currently sharing with these other 10 beautiful people online at the moment, and this interaction between us. Some of us are passive, we're listening. Some of us are trying to digest what Katina and Michael are talking about, and others are going, right on, Michael, I've got a good question for you. Is time a wave or a particle? Like, people are coming together to share, to give, to impart, to learn. But in fact, we've moved away from the fundamentals of why we exist, as what you've said to me, what I've learned from you in the last 6 weeks, towards this, how do we use one another to create productive movement, to generate transactions, and the game, am I right? The gainful game. How can I wallop the most out of somebody or the people I'm supposed to be serving? And what you're arguing through your philosophy is, heck, to hell with the generation and acceleration of the billions, right? What about us? What about the public interest in its guts? That's what your philosophy, I feel, is about. And I just wanted to extrapolate that out. But time, I'm looking at some screenshots of my studies in systems of innovation. It's all about chronos. It's all about documenting over time, the diffusion of innovation. I look at this linear view, as you're saying, and I look at these curves, and I look at the saturation curve, that point where everyone has a mobile phone. And guess what? Most of the population in Hong Kong have 2 mobile phones. We can saturate the market and then go some more. But if we don't interrupt these diffusion curves, we're not going to make more money, Michael. So we've got to disrupt and interrupt to create more of the productive movement that suits us. And behind what you were talking about in our first series of gainful game is knowing the players in the value chain, the intent of the players in the value chain, the manipulation of the markets in the value chain. And finally, one of the major points you made was, do you know what? We are so powerful as individuals in this public space. How are we going to institute what we want to do through our behavior? We are just as powerful in this gainful game, except we sort of disempower ourselves by believing things are truth and things are fact, when in fact they're completely, absolutely the opposite. So we've lost our ability to detect and understand what is truth. Is this page that I'm reading right now on, truth? Is this correct? And so one of the fundamental things, I remember being a student in my first year, and we were doing discrete mathematics, and we had to learn truth tables. And when the professor said, truth plus truth is false, right, I went wham, wham, wham. What do we call it? It's this exclusive disjunction. Truth and truth is false, right? Yeah. Which did my mind in. But it's almost like, I know this is not the perfect analogy, but now it's like, this person's telling me this and this person's telling me this. Boy, I'm not sure I'm going to believe it. What do we have left as humans, given this overload of information, Michael, in determining what truth is? What can we look to determine truth?
Well, the question there is, you've talked about the gainful game, but I think that this is the way in which what I call thingified value in motion. This is the motor. This is the motor of the gainful game. This movement of reified value, and you can say money, bloating itself in its circulating and keeping everything else in motion. So there's an intermeshing between physical motion and physical movement of things, which physics and technology is concerned with, intermeshes with the movement of this reified value, which bloats itself on its way through its circuits. And the faster it moves through its circuits, all the better, because it throws off more profit. But to get back to this time thing and this mathematization of the world for the sake of, it's a mathematization of the world for the sake of controlling movement. And so you need cause and effect, And in line with cause and effect, you need a linear time, which just counts off movement and registers it with some sort of clock. So in that sense, time is derivative of the movement, not the other way around. You have first the basic phenomenon, or the basic set of phenomena, are all kinds of movements. And time just figures as the counter, which also makes it clear that in this sense, time is for us who are dealing with movements in the world. So time itself is, in this mathematization of the world, it's dictated by this will to master movement of all kinds. And that's why you have, which means it has nothing to do with truth, because it's merely a parameter. It's merely a counting of time for the sake of mastering movement. And that's why you have a criterion for truth in science. Science must be predictive. And in that sense, it's also very useful. And this is the source of pragmatism, American pragmatism in philosophy. And empiricism already starts with Bacon, with the Anglo-Scottish philosophy way back 16th century. These things are dictated by this will to master movement. And that's why we say a science which cannot predict is useless as a science. So you have, for example, which you already mentioned, with the Einsteinian relativity theory. So what's the use of it? And this question crops up all the time. And say, well, that's all very nice to have these wonderful speculations about time and the way it fits with spatial coordinates, but what's the use of it? And so the scientists come up and they're pleading for funding, and they're always saying, well, one day something will come of it. And as just one example, you can take the GPS system. Everybody relies on GPS. It's really practical, because if you're driving a car, you don't want to drive it into the river, and you want to get to your destination. So this is a way of mastering your own movement in a car from one destination to another, from one place to another, A to B. Well, how does Einsteinian relativity come into that? Well, it just turns out that you've got all these satellites up there whizzing around, and the GPS works by triangulation of certain the certain objects on the ground. So this is cars in this case, and it can pinpoint the spatial location in these three spatial dimensions via the positions of the satellites. But it can only do so on the basis of the signals. Okay, the signals. But the signals travel at the speed of light. So in determining the position of a car on the highway from the three satellites, or the four, say three satellites, you can pinpoint it. You have to account for the speed of light, because the signals from the various satellites are at different distances away. So there can be a small error coming in because the signals are traveling at the speed of light, and you have to then bring in a relativistic correction to the determination of the coordinates. So you say, yippee, yippee, we have a practical use for Einsteinian relativity. Isn't that wonderful? Isn't that wonderful what science can do for us? But when we say, what is the truth of time? If we're looking at it from this angle of why it's necessary to have this conception of time as a simply counting of movement, it's not true, but it's a fact. It's a fact that we measure time by using clocks, but it doesn't say anything about the truth of time.
Mm-hmm.
So what is time itself? I think I'll just skip then to...
Michael, can I interrupt? Because there's two questions that are burgeoning here
Yep,
in the chat.
okay.
And I know you can't see them. The first is by Eusebio Sconavacha and the second by Edward Zinka. So Eusebio is from the University of Baltimore. Eusebio, you can unmute and go for it. And show your video if you want to.
I know you miss my beautiful face, Katina. Hi, Michael. Fantastic.
Hi.
Appreciate your thoughts on this. I work in information systems, and a lot of time the study I did on mobile technologies always has to do with time, space, and interaction, right? And I'm a bit unsettled at the moment when I see some people talking about or advocating towards what they call an ontological reversal, that the digital entities are shaping the physical world. So you have the cyber-physical interaction of digital, and human experience now becomes equated to computed human experience. So the moment that you're talking about GPS, or you're talking this, or all the conversations that we have, or all the movements that we make are being mathematized and are being computed. And I do wonder, it is something we should be comfortable. I don't feel particularly comfortable, I'll tell you that, with the idea that we converge or we reduce human experience to anything that can be computed. And this computed human experience is what shape our physical life. And that concept, to me, it's disturbing. So I'd like to get your thoughts on this.
Well, the basic thought is something that I spoke about with Katina in our first conversation. We talked about the two very different paradigms of movement, which gave rise to two very different understandings of ontology, two different ontologies. And what I laid out there and we spoke about was that the science and the technology that you're talking about is all based on a very, very simple paradigm, namely the paradigm of productive movement.
Mm-hmm.
And Aristotle is the father of that. He's the guy who works out the ontology of movement, which you have a power, or we say a power or a force, a dunamis. It goes to work. This is energy towards an end, which is the product. And this extremely simple, there's a very simple, you could say childish paradigm, is the one which underlies all science. I say all science, right to the very day, computer science, anything you'd like to name. And what I introduce in contrast to that is another extremely simple paradigm, and that is the one of interplay. And with the interplay, you don't have a productive movement of going from a starting point, a force is set to work and you get to your end, but you have an interplay between many different starting points. And in this case, you can say, okay, let's take humans. Each of us is the starting point or the origin of our own life movements in the broader sense, not just physical movements, but the movements we decide upon and carry out or try to carry out in leading our lives. And we always then, because we're living in a social world with others, we are always associating with the others, so that any kind of movement we make in the world is an interplay with others. So we are always estimating each other in this interplay, and this interplay itself cannot be controlled from a single source, which is what the paradigm is for science, is that you have a know-how, you have a scientific knowledge of something, and with this scientific knowledge, you can then control a movement. If you have the situation of an interplay, and we could just say a dialogue, or even more simply, you just take the interplay on the market where a buyer and a seller meet each other and they want to sell something on eBay, then they enter into an interplay with each other, and you can't say in advance whether the sale will take place or whether it won't take place or at what price it will take place, because it's in the interplay itself that all these things come about. So you can't predict what's going to come out of it. And even more so when you have conversations going on between people, speaking is also a kind of movement. So when we're speaking with each other, we are saying something, and we're also estimating what our interlocutor is saying. We're listening, hopefully, and we say,
sometimes I wonder in my classes,
that's a good point, or it's a bad point, or it's nonsense, or but the way the conversation runs in this interplay is not subject to any mastering point of origin that can control this movement. So this is what I want to bring into play as the alternative. You can work out the ontology of this kind of movement as opposed to the ontology of productive movement, and then what you have with this switch, if you think it through and develop it, then you have a different view of the world. So I'm concerned with how do we gain an alternative point of access to the world which isn't bent on control and mastery of movement, and mathematization is wonderful for that. How do we conceive with our minds another way of being in the world that isn't fixated on mastery, which has to be receptive to the other and to have a power play with it.
Right. And also I think the point of the fixation on trying to maximize economic output on any or any type of production output on any type of interaction, like you see as a system that your point is, where the ultimate goal is to minimize input and maximize output into those interactions. And what output is seen is basically productive output. And then when you start to use the digital reversal with ontology, saying this is it's almost the ultimate reflection of that ontology of productive time or time is a. So it's fantastic. It's really interesting to challenge the initial ontology that actually I think is giving how can I say basis for thinking in such a way that you are mathematizing absolutely everything, including the human experience. So fantastic. Exactly. Thank you.
That's exactly what I'm proposing, is that, say, when we refer to economic movement, productivity, cost efficiency, all these things, this is all pushed. It's all being borne by what I call the absolute will to power over movement, and what I call the gainful game. Another word for that is capitalism. I call it the gainful game for good reason. But anyway, if you think of the gainful game not from this productive point of view, from the point of view of this productive paradigm of movement, but from the point of view of interplay, then it could be that we in our minds, in our mindset, can see this gainful game itself in a totally different way, and this is really what is revolutionary, or the revolutionary possibility in philosophical thinking, is that we can, through thinking through these very simple phenomena, we can gain a different way of thinking very, very elementary phenomena in the world, so that the world looks differently. It's another world because our mind sees it differently. Absolutely. And if you go back and the case study I would take there is look at the transition from the end of medieval times to the modern age, the modern scientific age, which is now the cybernetic age, the age of the cyber world, where the algorithms are doing all the controlling. This paradigm, this was a paradigm shift, that the way in which the mind actually saw the world on a very, very deep level switched. It switched, and we live in it. Because we're living in this world, we can't see it. We just take it for granted, and anybody who starts questioning it is treated as a nutter. As somebody who's really not really.
I see Katina there. Katina, this just reminded of our good friend Pat Scannell, isn't it? Disruption of thought. Absolutely, yeah.
This is, Michael, amazing, because you know what? I think in the last 6 months, COVID has acted to shift something. We are all finding ourselves in different locations, in different contexts. You know, I wake up now. Of course I think about my work. It's the first sort of thing after I do my routine that I think about, connecting with my colleagues. But you know what? I've never looked at the ocean the way I've looked at the ocean at the moment. I've never looked at the earth as a whole unit, breathing oxygen and nitrogen and all of these other compounds like I have before. It's preservation, my children and their future. But the area and space around me and my colleagues and my friends. It's like there's something that's happened. Things have become more vibrant because I no longer am running to make sure the hockey stick effect takes place. I'd love the hockey stick to take place as a byproduct of earnest and authentic and loving work between people. But in fact, I'm looking outside and thinking, oh, it's raining today. I actually see the rain, Michael, because I'm not fixated on the typing. And I think we have a chance here through this public interest tech to say it's not about the tech, it's about seeing. The public interest is about seeing what's important to be seen. It's not about someone directing you. Now you will make more productive movement and you'll be a cog in the wheel and you will do this. That was the Industrial Revolution stage. I think we're going to see a shift of a huge magnitude if we can find it within ourselves to pause and say, wow. It's what you said in the first video. You said, wow. And it is the wow. It's not about us existing for the sake of producing more cogs in something or more artifacts or more units of production. It's about connecting on a scale that makes us human, that allows us to be human, that allows us to see, right? And not to see through. These things are making us see through each other, almost to a point where we've developed the inability, right, to actually interpret someone's facial expression. We used to be able to see whether someone was happy, sad, angry, ecstatic. Now we can't because we're bombarded with this stuff in the ether.
Was that Katina? Let me ask my phone.
Go.
No, I'm saying whether you're happy or not. Let me ask my phone.
Yeah,
but Katina knows the story that once I was at ASU and I saw a few chaps leaving a restaurant and they were saying, can you imagine the next swipe I do can be the mother of my children? And then that struck me with the danger of algorithm delegation. I have 2 kids. I love them. I have a wife. And one of the most beautiful things of my human experience has been meeting my wife, marrying her, having a kid. And suddenly, part of that process, I'm delegating to an algorithm. And this is scary, to be honest, in terms of, because it's more efficient. So fantastic. Thank you for bringing this up.
Thank you, Eusebio, for that intervention. I've got one more, Michael. I'm sorry, at least one more. Okay. Edward Zinker, whom I wasn't able to get to 2 colloquiums ago. I think it was Colloquium 5. Edward, if you want to unmute, let me know, or just unmute, and thank you so much.
Hi. Hi, Katina. I'm here at ASU in Core Hall in Tempe, and it's a beautiful day today. And looking at the chat sequence, Toby had some very good comments, insight that I played off of. And let's see, she talked about currency, movement, and money, and that's the flow of what's being discussed, and technology, and we talked about productivity. And so then I commented, it seems to me the ones who own the float, aka movement in time, are the ones who also own the printing presses. And I'm intimating there, play on words, not only printing presses printing money, the currency, but also printing presses printing the books, the ideas that drive the technology. And I don't know if that is I don't know if I can boil that down to a hard, simple question for you. It's just, the float, the movement in time, the ones who own the means. Just wondering if you, based on your background, have a comment on that.
Movement and time. If your question is about movement and time, what I've been talking about is this linear time.
Right.
And this linear time goes hand in hand with cause and effect. And if you're living in a world which we are living in, which is under the rule of the will to master movements of all kinds, then you need a linear time which counts off movement, and the movement itself is conceived as cause effect. And you've got to get to the causes and see the effects, and you can use mathematics to see what comes out of it. And what I just discussed about interplay, which interplay defies this mastery over the interplay among us players as humans in the interplay. We bring our powers, we bring our abilities into interplay with one another, often against one another. We can be really nasty. But in any case, it's an interplay. And it's not controllable. You can't have any point of origin from which you can control it, even though you try. I mean, the algorithms are trying to do that, but they come up against this thing, this phenomenon, I call it phenomenon of interplay. So it's up to us to say, what is the truth of this phenomenon? We know it as a fact. Like we know it as these facts, we know that the conversations go on and we understand it all well. But what's at this deeper level that I call the ontological level, which is the level at which you get to the truth. And I say there that when you approach the phenomenon of interplay as a kind of movement, then this linear time is useless. This linear time, which goes hand in hand with cause and effect, is useless. Chuck it out. We have to change our mind, which is hard because it's to do with extremely elementary things. We have to change our mind through another way of thinking, which is a more appropriate to this phenomenon that I call interplay. What we do with one another, in play with one another, in all sorts of social interplay. And that's why I don't call it social interaction, because social interaction is too much in this mode of, I act, I get a reaction, and you can put that in sort of pattern, and then you can develop a systems theory. So what I'm saying, it goes really deep. If you want to look at this phenomenon of interplay, which defies mastery, it also means that your concept of linear time is also useless, because it's not to do with just cause effect, but of the interplay, how we estimate and evaluate and esteem each other. That's the baseline. And for that you need another understanding of time. And this understanding of time is what I call three-dimensional time, which has the well-known dimensions of present, future, past, but they're all in a line, right? All nicely lined up because it's all it's interested in is following the cause and effect. But in fact, the three dimensions are free. They are free three dimensions. So you don't have them in a line, but you have three independent temporal dimensions. You can call them future, present, and past, but they too are in interplay with one another, in the sense that they offer us humans the possibility, in thinking about interplay, that we can actually move through these three dimensions, not in a linear way, but we can actually move freely from one dimension to another dimension, without worrying about any Einsteinian relativity theory about the absoluteness of light, the speed of light, which is the criterion for all physical movement since relativity theory. We're not restricted to acting like a light beam with our minds. Our minds are three-dimensionally temporal. That's why we don't need to take relativity theory into account with the speed of light and say, okay, the sun is out there. Okay, well, actually it's nighttime here, but during the day we got the sun, and the physics tells us, because of the distance of the Earth from the sun, that it takes 8 minutes for it to get here at the speed of light. So it's dependent. The signals we get depends upon the speed of light. But the way our mind works, I can think of the sun right now. I can think of the sun right now where it is, and it doesn't take me 8 minutes to think of it. I can just think of it, and I can also think of the sun rising tomorrow. I can think of the sun in its motion tomorrow, rising above the horizon, and it doesn't. I can move to the future, and I can think of, and I can also simply move to the past, how the sun set yesterday evening. I can see them all. And I can hop from one to the other and faster than the speed of light. So I'm not restricted there. So this is this is one of the consequences of rethinking time, not as this linear marking off and counting, and tied to the speed of light, this absolute movement of the speed of light, but opening it up so that we are able to move, and we already do that without taking it really seriously in an ontological sense, that this conception of time as three-dimensional and open is the one which gives the truth of time. And it also solves this whole paradoxical business about Zeno's paradox, about the arrow that cannot move because at any instant the arrow is frozen in an instant in its motion, so I can't move. This is the nub of Zeno's paradox. But if we have a different conception of time, then this plays no role whatsoever. Because the time actually is what enables all sorts of movement rather than the other way around. Up until now, right from the beginning of the Greeks with Aristotle, right through and right up to the present day when we got these really incredibly accurate clocks, it's all linear time, and it's all there because this conception of time as linear is wonderful for controlling movement. But if we open it up, then we have a different conception. We have a different conception of time, and we have a different conception of movement, which doesn't have to be mastered. And we don't have to worry about Zeno's paradox.
Michael, sorry, Ed, I've got one more question. If we can go to Toby, just coming off that, stay with us perhaps. Toby, did you want to unmute? If you could, you're welcome. Just let me know in the chat, and otherwise I'll ask your question for you. There you go.
Sure. I can even turn on my video.
We can see you. Go ahead.
Wonderful. My question is, so science and technology have this basis of mastery of cause and effect. Is interplay possible with these tools? Can science and technology embrace this interplay, or are they foundationally not able to do that?
I think this conception of movement as interplay, and this conception of three-dimensional time changes the ball game quite in a very fundamental way. So it's not a matter of it's a matter of putting science and technology with its cause-effect relationships and with linear time, marking of time by clocks and organizing. Okay, it's putting it in its place and taking a step back from it, and saying, well, what enables movement itself? If we're not out to control movement and use linear time and cause-effect relationship to control it, but open up time to this three-dimensionality and see that it is only movement is only possible within time, within this three-dimensional time, because the movement we're talking about, we're not talking about movement kind of dissociated from us, but it's always the questions that I'm posing in a phenomenological way. It's always the way in which the phenomena show themselves to us, because we're the humans. We're the ones who are open to the phenomena, and we're the ones that try to make sense of the phenomena. So if we are trying to make sense of the phenomena, and these phenomena are in movement, so we're trying to understand all the various phenomena of movement. So this is something. How do we conceive movement for our mind? And that's where I come with to say that the mind itself is nothing other than this three-dimensional time. In fact, our psyche, our psyche, the mind is the understanding part of the psyche, but the psyche itself is nothing other than this openness for the world. And this openness for the world is not the mathematical or the mathematized access to the world, but is simply the openness for in this temporal three-dimensionality. So that, properly speaking, to see any kind of movement, if we just come back to Zeno's paradox. Mathematized, you say that because in the present instant, the arrow in flight is at a standstill, it can't fly. Well, I say, no, that's not true. That's not true to the phenomena. And in this case, the phenomenon of the motion of the arrow flying through space, right? Because we have no problems. We don't have no problem at all seeing an arrow in flight or a bird in flight. We don't have any problem. But why? We don't see the bird in flight at an instant anywhere. We simply don't. We see the bird, and we see also the bird with our mind's eye, where it will be and where it was. So we have three-dimensional temporal vision. Our mind, we ourselves are this three-dimensional openness for the world in this temporal sense, that we can only see the bird in flight because we are seeing is, will be, or may be. We don't know exactly where the bird's going to fly, but we can see that it's in motion somewhere, and we also see it in where it's come from. Although we know that it's come from somewhere, we might not know exactly, but it's nothing to do with being able to sort of pinpoint and pinpoint in an equation the flight of the bird. But in order to see the motion, the bird in flight itself, we have to have ourselves three-dimensional temporal vision. And if you say that to a scientist, they'll tell you you're nuts, because all the sciences are based upon sensuous perception, and the senses only see in the present. They only see in the present. Like, although everybody knows, if we only ever saw in the present, we wouldn't see anything at all, because we're always looking ahead, we're always looking back, and not just after the other in a linear fashion. We're looking back and forth and now all at once, which is completely unlogical. If you look at the principle of contradiction, which is the big basic principle of logic, according to Aristotle. And you won't find it just in Aristotle. You'll find it right throughout science, logic, mainstream philosophy. The principle of contradiction, that something cannot be such and not such at the same time. So it all depends upon how you interpret time. And if you have time just consisting of, instants of time flowing through a now and going into the past, if you've just got that, then of course there can't be anything as what's now, and you see it because the senses are the thing that determines what you see now in this instant. Then of course the principle of contradiction holds. If I see this finger, then I can't see the other finger at this moment. I've got to turn my head. But if we're seeing it in this three-dimensional way, then the simultaneity means something completely different. It doesn't mean the simultaneous at a now instant. It means a simultaneity that we see things together. We see three dimensions of time. We're looking into three dimensions of time all at once. And all at once is a nicer way of saying simultaneously, to get rid of this. And simultaneously is something we always think of, simultaneous. Now, this happens now, and this was, I'm banging on the table, and I'm with my left hand, my right hand, and they're simultaneously in the now. But I'm simultaneous. I can think of the kitchen where I'm going to have a cup of coffee, or right now, no problem. I can think of this movement of going into the kitchen with. I don't have to actually do it and sensuously do it. I can conceive it, and this is the wonder of our minds, that they are our mind, which we share with one another, is three-dimensional in this temporal way, all at once, and it's not restricted by the absolute speed speed of light that was laid down as a postulate by relativity theory. And they're still trying to work it all out, right? That's why they got this hadron collider, and you've got these gravity waves and all this stuff going on without looking at the simplest things of asking, what is this time? And it's a big problem for them, because if you don't have the time, then you don't have the equation. If you don't have the equation, then you can go home. You've lost your job. There's nothing for you to do as a scientist if they take your equations away from you, then you're a dead loss. There's no science. There's no technology. You've lost this mastery. But we've got to take a step back and lose this mastery. I'm not saying chuck it all away, but we have to have a new mind, a revolutionary other mind, to be able to see the world differently in a more open way that isn't tied to this mathematization. We've been on this circuit for 400 years, 500 years. We just got to take a step back.
Do you know, Michael, as we close with a couple of minutes to go, and don't go off Edward and Toby, that's what we're hoping to do in this new Public of Interest Technology degree that's a Master of Science, quite interestingly, is to develop people who not only think outside the box, but will come with different views of the world, will see things differently, will challenge the rubrics of the last 400 years, will ask the right questions for today by looking at the future, looking at the past. We all often talk about the now casting, the back casting, the future casting, foresight studies, anticipatory governance, participatory approaches to development and design. But we want to be able to see the user and the needs of the individual, the person. I don't want to even call him a user. That's techno speak, right? I want to call him the person who needs something, and we all need something. And collectively, we may need certain things in particular communities, but we're hoping to develop a process by which what becomes more attentive is not the bottom dollar. I mean, money is required in the economy, obviously, but it is about coming together at that important interplay where we say, I need something, like these ancient communities once did. They would give when they had enough to give. If someone was in need, you weren't going to let your neighbor die. And that's the public interest. It's the needs. And I think you've given us a great elaboration over the first 2 hours of us hearing you speak at the Colloquium. Hopefully we can invite you back maybe mid next year to continue on what you've started today. But we'll continue our video series, of course, and we can invite all of these wonderful people. Jumana Bugazela, the president of Pivot for Humanities, with us, an amazing scholar in her own right, who talks about the importance of humanizing and professionalizing the STEM practices so that we don't have this phenomena of just worrying about hockey sticks, but what else? The interplay of people together. Eusebio that you met, who's in digital business and so much more, information systems as well, but predominantly business. Ryan Radcliffe, thank you again. I think this is your second time at the Colloquium. Tara Hestone, thank you for coming back. Toby, thank you for coming to every single one. To our logistics team, Melissa Waite and Cindy Dink, thank you. We couldn't do this without you week in, week out. And to Dr. Roba Abbas, who was with us, Edward Zinker, thank you as well. You're right in front of me with the mask, which is the right thing to be doing at the moment in Arizona. We had Professor Robert Cook-Deegan, a medical doctor who's also working in our DC office at ASU in the School for the Future of Innovation in Society. Martin Comiso as well, one of our PhD students in the Human and Social Dimensions program. So there is so much yearning to hear people like you, Michael. I hope you know that we appreciate your time. And to everyone that stayed on right to the last minute, thank you for your excellent comments. You've got chats saying thank you, Dr. Eldred, and thank you for your humility. You're a very amazing human being with many qualifications. We didn't rattle them off, but just thank you so much for the time you've given us today.
Yeah, thank you very much, Katina, for inviting me, and thank you to all the participants for the very lively chat. I think we got some thoughts into motion, which is the main thing.
Invaluable. To everyone, see you in 2 weeks with Professor Pascal Zachary. Bye now, everyone.